So this is Engineering Statistics and Linear Algebra 18 EC 44 Module 2 Lecture 2 Multiple Random Variables. We'll be dealing today with the bivariate expectations. In the Lecture 1, we have studied the introduction and also the basic things about the bivariate two variables till the time we considered the independent variables. Okay, so for two different variables, what will be the expectations is what we will see in this class. So the expectation operator applied to the bivariate random variable is written like this, where the difference is over here for a single random variable. This will be gx, and then it will be gx here and f of xx. Now, because this is g of xy, this will be g of xy, and because we have the two variables, we'll have the PDF also associated with the two variables, f of xy, x comma y. So g of xy is an arbitrary function of two variables. It can be mean, it can be covariance, it can be correlation, or whatever it is. G can be any function which corresponds to the two variables. So if g of xy happens to be a function of only one random variable x, then we'll get back the same equations which we have got there. So that means if we remove this y over here, then only gx will be there here, and this will be, this will become gx, and it can come out over here, and this total thing will just become, you need to differentiate it with respect to y. So this quantity over there here will be just fxx. This quantity over here will be fxx. So we are using what you call the equation 3.17 was used to obtain the PDF fxx. So this means that all expectations introduced with a single random variable, that is mu x, mu y, sigma x square, sigma y square, are included in the bivariate random variable. So by definition, we can use what is known as correlation of x and y, which is nothing but the expected value of the product of x and y. So whenever we use the term correlation, it just means E of xy. That means the two terms here, the gxy will become equal to xy. Okay, it's product of x and y. So at that time, the g of xy will become small xy over here, and this is what we will have for the correlation. So the correlation is often used with zero mean bivariate random variables. Generally, whenever we consider the mean of the random variables to be zero, such as those suggested in the figure 3.1, it may not be obvious how correlation as expressed in the integral relates to the figure. However, the idea is very straightforward, and we see that expectation is conceptually the averaging. So, integration is just nothing but averaging only, and that is why we can almost write E of xy is almost equal to 1 by n sigma xi yi. So under that condition, we can have this quantity to be either greater than 0 or less than 0 or equal to 0. So if it is greater than 0, then we call that as a positive correlation. And if this quantity is lesser than 0, then we call it as negative correlation. And if this value is equal to 0, he has mentioned it as uncorrelated, but rather you cannot say it as uncorrelated. You can as well say that they are orthogonal to each other. We'll see that a little later, but he has put it here as uncorrelated. But again, he's trying to define what is uncorrelated variables separately also, which is not same as this, right? So I would rather say that here it should have been orthogonal rather than uncorrelated. Okay, so positive correlation, negative correlation, and orthogonal to each other. So if a bivariate random variable do not have mean of 0, we generalize the correlation in the 3.37 and define the covariance. So if the mean is not 0, then we write the covariance. If the mean is 0, yes, you can always say that this is equal to uncorrelated. So in the case when mean is existing, we generalize the correlation in 3.37, which we have mentioned earlier here, to mean the covariance, and at that time the covariance of xy is equal to E of x minus mu x, y minus mu y. So if mu x and mu y both turn out to be 0, covariance and the correlation both will be same. If mu x and mu y are both zeros, then covariance and correlation will be both same. So applying the rules of linear operation in the 2.58 and 2.59 to the bivariate random variables, then we can just expand this over here. Xy, you can expand that bracket over here. X minus mu x into y minus y, you can multiply these two terms, and then we will get this xy minus mu xy minus mu y x plus mu x mu y. So whereas you can apply the what is that addition rule, that is you can separate this out, and that is what it means by this. And also if it is multiplied with a constant also, you can take it out. Mu x mu y can be considered as a constant. So E of xy is written as it is, whereas E of mu xy will be mu x is constant, taken it out, and then we have Ey. Similarly, what you call E of mu yx will be mu y of E of x, and the expectation of the constant value only will be the constant itself. E of a, small a, will be a itself. So generally we what you call, this is nothing but the mu y, and this is nothing but the mu x. So therefore we will have one of the term cancelling over here, and only one of the term will remain, E of xy minus mu x mu y. So this is mu y and this is mu x, and hence we will have the total term to mean only this. So in case when we, when do we say that we have x and y to be uncorrelated? So x and y are uncorrelated only if the covariance is equal to 0. The covariance is equal to 0. So uncorrelated is associated with covariance equal to 0. And as a definition, we can say that if x, y are uncorrelated, then we'll definitely have, okay, when this is equal to 0, then this will be equal to this, and that is what we have mentioned here. If this is equal to 0, this is equal to this, and we have the same thing over here. Then we come to orthogonality of x and y. If we find an application in which the correlation is 0, that means E of xy is equal to 0, right? E of xy is equal to 0. Then we say as a definition that xy are orthogonal. So uncorrelated is, by definition, covariance is equal to 0, whereas orthogonal means correlation is equal to 0. So when correlation is equal to 0, the covariance value will be equal to minus mu x mu y. However, if both these are, are either one of this is 0, then we'll get the covariance also as 0 at this time. Then how do we, consider the independence of x and y? So it's rather very interesting to check the, correlation with the independence. We can try to see how the correlation and the independence are related to each other. So we can try to write g of xy as x to the power n, y to the power m. And at that time, we will have the quantity over here, which is the value which is e of e of x to the power n, y to the power m is equal to double integral of small xn y m, and the what you call, this is fx y xy, and because they are independent, you can separate them out. If you say that they are independent, you can separate them out, and if you separate them out, you will get fxx separately, xn separately, and this will be a separate integral, and this will be a separate integral. At that time, we will have e of x to the power n, e of y to the power n. So if x and y are independent, then E of xn ym will be E of xn multiplied by E of ym. So, however, uncorrelated random variables x and y speak only to the case where n equal to m equal to 1. So, when we say uncorrelated, then we say that it is n equal to m equal to 1, and at that time only the covariance value is equal to 0. Okay, not that this will be equal to this. This will be the case when they are independent. So it just means that the general conclusion is that independence implies uncorrelation, but the reverse is not true. So whenever we talk about independence, there might be, uncorrelation, but the reverse is not true. So when mu x mu y will be equal to 0, then E of x y will be equal to 0. So independence includes the implies or includes uncorrelation, but uncorrelation does not imply that they are independent of each other. Okay. Now, when we talk about the correlated x and y, then we come to what is known as the correlation coefficient. Correlation coefficient is written as rho of xy, and it's denoted by rho of xy is equal to covariance xy divided by sigma x sigma y, where each one of this is a standard deviation. So if you consider back the covariance in 3.38 and divide it by the two standard deviation of then we will have the value which correlation coefficient defined over here. So we'll get at that time E of x minus mu x divided by sigma s plus r minus y minus mu y by sigma y whole square. So this should be greater than 0. This should be greater than 0. Expectation is always, you can say, positive. Okay. So this inequality remains the same after the square is expanded. So if you expand this, we'll get the value of this. Okay, this square plus 2 into this. At that time, we will get this quantity. So now, this quantity is nothing but E of x minus mu x by sigma x whole square is nothing but 1. Similarly, E of y minus mu y by sigma y whole square is also 1. Because expectation of y minus mu y will be the value which is square will be the value which is sigma y square. So sigma square, sigma y square will cancel. Similarly, expectation of x minus mu x whole square will be sigma x square. So sigma x square by sigma x square will cancel. Hence, it will be equal to just 1. So this will be 1, this will be 1, and this quantity is nothing but the the quantity which is written over here, and 2 is there as it is. So 1 plus r minus 2 sigma xy plus 1 greater than 0. So if you try to simplify this, then you'll get sigma xy is, if you take this one, this side, then the what you call direction of this arrow is going to shift. So therefore, we'll get sigma xy is lesser than always 1. So what you call, if we consider the sigma xy is equal to plus or minus 1, then what you call, then we just say that is the maximum possible correlation coefficient equal to 1 will give us that we will have the value of covariance xy is equal to sigma x sigma y. So now we can consider the equation y is equal to ax plus b as an equation and consider whether we will get correspondingly what is the value of the sigma xy under those conditions. So if y is equal to ax plus b, then starting from 3.38 and using 2.60 and 2.61, then we'll get the covariance of xy as E of x minus mu x into ax. This is y minus mu y. Y minus mu y will be, y is nothing but ax plus b, and also mu y will be a mu x plus b, and that's why minus of mu y will be the value which is mentioned over here. So you can just take out the value a there and try to simplify and write it at that point. So x minus, so you can simplify this over here. So plus b minus b will cancel and a is common, so a comes out, x minus mu x is what we'll have. So this, because this is a constant, it can come out totally e of x minus mu x whole square, and this quantity is sigma x square. And the standard deviation of y is, sigma y is equal to the standard deviation here is plus or minus of root of a squared sigma x, that is plus or minus a root of sigma x. So finally, combining all this, we will see that the correlation coefficient is covariance. The correlation coefficient is equal to covariance, which is the value which is a sigma x square divided by the value which is nothing but the what you call this itself, which is the sigma y. Sigma x is not there at all. Okay, is equal to what you call sigma x. Sigma x will be sigma x corresponds to sigma x and sigma y corresponds to this. So therefore we'll get sigma x square. So this sigma x square, this sigma x square cancels, and a and root of a square again will cancel, and hence we are left with plus or minus 1. So that just gives us that the sigma xy has the limits which are between -1 and +1. Okay. So now let us take some examples. Let us assume that the means are mu x equal to mu y is equal to half. Then the correlation will become E of xy is equal to, so to say, the value which is 0 to 1 x dx, 0 to 1 y dy equal to this. If you try to integrate, it will be y squared by 2. This will be again x squared by 2 with limits 1 and 0, limits 1 and 0. So overall it will be just equal to 1 by 4. So this range of values is given in the figure, which corresponds to 3.7a, 0 to 1. So we see in this example that the random variables are uncorrelated because of the reason that we have 3.41. Because E of xy is equal to mu y is equal to 1 by 4. Therefore, the covariance xy is equal to sigma xy is equal to 0. Then from the figure 3.8a, which we have considered earlier, the bivariate. So this is the discrete case. The bivariate PDF f of xy is shown in the figure 3.16, and the two PDFs fxy and fyy are shown in the 3.23 and 3.24. Then from 2.44 we can find the mu x and mu y to be equal to 1, 1. This we have already found. Mu x equal to mu y equal to half. So from 3.37, which is the equation which we have written over here, right? This equation which we have written over here, we can try to solve that and try to write the values. So xy 1 by 4. This will be the total value which corresponds to f of xy x comma y, and that will be 1 by 4 del x del y plus del x minus 1 del y. So if you simplify this over here, plus the value corresponding to the total, this is 2 terms, the other 2 terms are over here, dx dy will be there. So this we have already found out in the problem associated with the figure, which is 3.8a, might be 3.3 or 4, which we have considered in the last class. So let us see that whether we have the same thing there. Yes. So this is the one I think you might have. Yes, this is the one which we might have written over here, right? This is the equation which we have written there, corresponding to it. Okay, this is the one which we have. So here we have in the question number 5 a bivariate PDF for the discrete random. So in between the video has come there somehow. Okay, so this one is the one which we are trying to use for the numerical which we have just considered. So that is the one which we have written over here, and if you try to simplify that, you know, we will get y into 1 by 4 dy plus dy minus 1 dy, because we need to integrate all that, and we'll get only 1 by 4. So thus in this example, as in the previous example, x, y are uncorrelated because E of xy is equal to mu x mu y is equal to 1 by 4, and then we'll have the covariance of xy is equal to the sigma xy will be equal to the value which is 0. Okay, so covariance will turn out to be 0 because both are same. In the earlier example, you know, we have considered the what you call E of xy is equal to 1 by 4. Here we have considered the E of xy is equal to 1 by 4, and mu x mu y is also equal to half and half. So mu x mu y will be equal to half into half. That will give us 1 by 4. Hence, since both are same, then we say that they are uncorrelated. So another example which we'll consider is mu x is equal to 1 and sigma x square is equal to 2 and mu y equal to 3 and sigma x square is equal to 4. And if we have this case, then what are the values of the covariance and the correlation? Okay, so the covariance is equal to sigma xy, so to say the rho xy, sigma x, sigma y. So that is equal to this multiplied by root of this and root of this. Root of this is 2. 2 into 0.5 will be 1. Root of this will be root 2. So that will be root 2 into 1, and hence that will become 1.4142. Also, the what you call correlation will be equal to the covariance plus mu x mu y. So covariance value we have found out over here 1.4142, and this quantity is nothing but 1 into 3. 1 into 3 will be 3. 3 plus 1.4142 will give us 4.4142. Let us take some of the other examples also. The mean and variance of the random variable x are -2 and 3. The mean and variance of the random variable x. So this is the mean and this is the variance of x, and mean and variance of y are 3 and 5. The correlation coefficient is this. What are the covariance and the correlation? So covariance is nothing but again the correlation coefficient, which is nothing but rho xy multiplied by sigma x, sigma y, which are the standard deviations. So this value is given to us as 0.5. This value is, root of 3 and root of 5. Okay, root of 3 and root of 5. So therefore, root of totally 15, and that will give us, which is nothing but 2.7111. Then we can write the correlation E of xy is equal to covariance of xy plus the mu x mu y. So covariance we have found out from here, and mu x mu y is -2 into 3, -2 into 3, and that will give us this. So therefore, it will be -3.2889. 19th problem, the vice versa is done over here. Mean and variance of x and mean and variance of y are same, which are given there. Only that E of xy is given as -8.7. What are the covariance value and the correlation coefficient? So we can find covariance because we know this, and we know the mu x, which is -2, and mu y, which is 3. So from that you can find -8.3 minus of -2 into 3. That will give -2.7 as the covariance. So the value of the correlation coefficient will be covariance of xy divided by sigma s sigma y. That is covariance is minus 2.7, which we have found here, and this is root of 3 and this is root of 5, and that is what is joined together and written as root of 3 and 5, and hence we'll get minus 0.6971. Then the what you call 22 is x is a random variable with mean and again the standard deviation here, not variance. So this square will be the variance. Y is the random variable again with mu y equal to 6 and standard deviation is equal to 7. Correlation coefficient is 0.7. If u is equal to 3x plus 2y, what are variance of u, covariance of ux and covariance of uy? So covariance of xy is what we can try to find out. Covariance of xy will be equal to the rho xy into sigma x sigma y. Rho xy is what you call the value. Is it given there? Rho xy. Correlation coefficient, okay, is 0.7. Correlation coefficient is 0.7, and sigma x is 5, sigma y is 7. 35 into 0.7 will give 24.5. So once having found this, then we can find the value of sigma u square. U is nothing but 3x plus 2y. So therefore you can write it as u minus mu u whole square, and u is nothing but 3x minus 2y. So you can write 3x minus 2y minus the mu what you call of u, which will give us 3 mu x plus 2 mu y as the value there. So we will get correspondingly this value to be equal to what you call, you can expand it over here. This is u of 3 rather 3 square. This you can expand it totally and try to write also u square minus mu u eu, and then all those things which will be just the expansion, and we can try to write there. So u square will be the value which just corresponds to 3x plus 2y, and hence that will give us 3x will give you 9x minus mu x square, and corresponding to 2y we will get this term over here, and this is the term which is the combination of those two. Okay, so you can just solve it in the similar way whatever we have solved. So you need to just expand this over here. It will be u square minus of u square minus of the what you call this quantity will give you the value which is e of u into mu u minus mu u into e of u plus mu u square. So that just means that it will become u square minus mu u square. So u square will give you this term and this term together, and mu u and mu u square will give you the quantity which is this. Okay, so that will be 12x minus mu x minus y minus mu y. So expanding that, you'll get y 9 sigma x square plus 12 of covariance of xy plus so this is naturally the covariance. 12 of this e of this quantity will be covariance. 9 of e of this value will be the what you call the standard deviation square, that is the variance of x, variance of y over here. You need to just substitute the values from there and try to write it. Similarly, covariance of ux will be, we need to write the two terms there, that is e of u minus mu u into x minus mu x. Again, you need to expand this over here, right? You need to expand this over here, right? You can make the long form of this, or first substitute for u in each case and try to find out the value. So separately you can find mu u also by finding the mean corresponding to this. Mean of u will be 3 of mean of x plus 2 of mean of y, and that will give us the value which is corresponding to mu u also. You can write it in that way and try to substitute the total thing, right? So he has written here 3 into x minus mu x plus 2 into y minus mu y uh, multiplied by the quantity which is written over here, 3 minus mu x. Okay, he is writing here for this, he is trying to separate it out. For this term he is writing this, and this he is writing separately, and that will give you 3x square, 3 sigma x square plus twice of covariance of xy. If you expand that, and you will get at the end 124. Similarly, covariance of uy will can be written as this, and corresponding to this what you call this same thing as this quantity over here, but only you are trying to multiply with this. So that will become 3 of covariance of xy plus 2 of sigma y square is equal to 171.5. So what is important is these are all short forms of solution, but the long form you can try to write each quantity and substitute and try to see the result at the end. So at the end we should get this, and we'll get that as 171.5. Then the 25th is xy are correlated random variables with a correlation coefficient of sigma equal to 0.8, mu x equal to 20, variance of x is 70, mu y is equal to 15, variance of y is 100. Then you can find the two different variables.